Yeah, so it's really a pleasure to have all of the folks here in the room because, I can see faces and not little black squares. So this is great. So really, so what I was saying is that we're at this kind of revolutionary time, and I'm going to keep an eye on the time so that and I'll cut things a little shorter because of the late start. So everybody gets to go home in good time. Okay. So, all right, so great. So I found these historic posters because at a certain point in time when cancer screening started, there was one cancer screening technology, and that was breast cancer screening. And there was, these are from the American Cancer Society, and almost one of their sort of founding principles was to get women screened for breast cancer. A lot of enthusiasm about breast cancer screening. Does anybody know how many breast cancer screening trials there have been? So I think it's about 8. How many of those were done in the US? 1. The first one was done in the US in the 1960s. A lot of enthusiasm. The trials have been analyzed every which way. But as time passed, of course, there became more tests for cancer, right? Colonoscopies, prostate cancer screening. And as more and more testing was done, people began to realize that the tests weren't always, simply beneficial. They were not always a good thing. And so this is a Wall Street Journal in 2014 article about overdiagnosis, the possibility that cancer screening tests could find cancers that would never have progressed to cause a problem. We learned that cancer is heterogeneous. It's not one size fits all. So that kind of enthusiasm kind of tracked downwards for a little while. And today we're here. We're at the point where kind of the code for detecting cancer signals in the blood has been cracked through the technology of liquid biopsy and the ability to interrogate fragments of DNA, methylation, even RNA in the blood. And so there's this excitement, and it's not a pie in the sky. There are products. There is at least one product, more than one, that is available. If you have $950, you can get the Grail test in certain health networks and in certain states. So it's happening, and it's happening fast. And this is really kind of the culmination, even though a lot of this work is being done outside of the academic enterprise because it needs very deep pockets. Culmination of the phases of biomarker development that were put out by the EDRN in 2000, where they really kind of ordering the sequence of studies that need to be done to show that it's worth doing a cancer screening test, from just very preclinical studies to actually, where you actually develop and find the marker, maybe animal studies, in phase 1 to phase 2, where you actually then run the test on known cases and non-cases. So you know they have cancer, so you get a sensitivity, but it's a retrospective, it's a clinical sensitivity. And then the third phase is where you find, in your back closet, or hopefully have collaborators that have stored blood. And a lot of these studies actually have been done in blood banks in Scandinavia, where big studies were done and a blood sample was stored, but also a couple of studies at Harvard have yielded data on this. Anyway, there was a study in Hopkins, the Baltimore longitudinal study of aging, where just blood was stored. And then you could kind of look and see who has cancer in a certain year and go back to their blood samples and see how long before that time the test becomes positive. Okay, then the next phase is then to actually apply it in a population of asymptomatic individuals, where you would use it in practice and see how many cancers you detect and how many false positives and what happens to people in terms of their follow-up testing. And the last phase is screening trials. Now, all of these phases have led to a tremendous amount of opportunities for statisticians. And I mean, I could do a whole talk in each of these areas. So for example, when doing prospective diagnostic performance studies, we have the whole literature on verification bias sampling, because you don't biopsy everybody, you selectively biopsy people. A lot of work in ROC curve analysis, ROC curve regression, and time-dependent measures of diagnostic performance. And then when you're looking in these serial studies at longitudinal biomarkers, you've got all these models of biomarker growth and transition from a non-cancer to a cancer state, so change point models. But then in the prospective setting, people, you stop evaluating people if their biomarker is high. So your longitudinal sequences are informatively censored. So there's work on informative observation processes. And then there's trying to understand the natural history of disease from interval sensor data. I'll talk more about this later. How do we learn about overdiagnosis? Need to understand the natural history of the cancer, how long it is latent, to learn of the chance that it could be overdiagnosed. And a lot of work on multi-state models. And then how do we design these trials? Some trials screen only for a few years because of expense, and then they stop and they follow individuals. So that's a certain kind of design that leads to a non-proportional hazard situation. So we have non-proportional hazards methods. And then when we want to put screening trials together, how do we put them together? What's an appropriate way to do meta-analysis? So just some of the really kind of cool statistical opportunities in this space that is very impactful, that impacts millions of people. So I'm going to show you some examples. So here's PSA. Here's the very seminal study from the Baltimore longitudinal study of aging, where people just came in and had their blood stored, and then they went back and they looked at prostate cancer cases, their historical trajectories. So obviously there was a big longitudinal estimation process that went on in these data, and it suggested strong potential for PSA as a biomarker for prostate cancer being the most common cancer in men, and particularly in African-American men. There's among African-American men, 5% in the absence of screening, 5% will die of prostate cancer. So it's really a very prevalent and seemed very promising. And eventually 2 screening trials were done, one in Europe and one in the US, and they did not agree that prostate cancer screening was worthwhile. And the Preventive Services Task Force gave prostate cancer screening a D, meaning do not do, about 10 years ago. And this led to tremendous consternation in the field because I don't have a slide to show you. This test had become very prevalent in the population, and the incidence of advanced stage prostate cancer had plummeted. It was actually rare to find a late stage prostate cancer at the time that the US Preventive Services Task Force said, don't do this test. How do we do a meta-analysis of these trials? So we worked with Alex to do actually not a standard meta-analysis, but a meta-analysis that accommodated the intensity of screening in each trial on each arm. So instead of just averaging across the trials, we had to acknowledge the fact that the US trial was done too late. It was done after screening had already become popular. And so the men in the control arm were also screened. And there was only a small amount of that contamination in the European trial. And essentially what we did with Alex was to develop a measure of the screening intensity on each arm. And I'm just going to show you one estimate of the screening intensity on each arm in the screening arm in the European trial and the control arm. So it's what we call a mean lead time, a restricted mean lead time, which is on that arm with all the screening and biopsy that was going on. What's the average earliness of detection on that arm? So we estimate on the ERSPC screening arm, men were being detected on average 4 years earlier. than they would have been without screening. And on the control arm with a small amount of contamination, they were less than a year earlier. But on the two PLCO, the US arm trial, on both arms, you can see that the lead time, the time that by which the cancer was being detected earlier, it was actually quite large on both of those arms. And so we conclude that really, we actually show quantitatively that it's really the difference in screening intensity across the arms, the fact that there was a big difference in one arm, big difference in the other, we show conclusively that this actually explained the difference in results. And the way we got these numbers was by fitting models, natural history models, to learn the latency of the cancer on each arm and to learn thereby the time by which the cancer was being detected early under screening. And this was published in the Annals of Internal Medicine and put to rest a lot of controversy across the trials, because ultimately when we combined the results, we learned that screening was effective, and it was similarly effective in the trials per year of mean lead time, but the lead times were different across the arms in each trial. So I give you, just to give you a sense of model-based meta-analysis of cancer screening trials. And if we go to CA125, a biomarker for ovarian cancer, this was the other biomarker that was in use, but not in widespread use, because it had not been, ovarian cancer is very rare. And even though there were products for doing this that were available to the public, it had not become as popular as in the case of prostate cancer screening. So this is CA125, similar studies, lower numbers, the cases, longitudinal studies, cases are blue, the non-cases are green. And this was the first personalized test using a biomarker developed by Steve Skates and colleagues. It was called the ROCA test. And what it did was it fit these longitudinal trajectories to cases and non-cases. And then when a new case came along, using Bayesian methods, predicted the probability, that was the posterior predictive probability for the new case of being in the blue class versus being in the green class. So it really was kind of based on the woman's trajectory, looking at a bank of training trajectories. Did the woman coming in, did her trajectory look more like a case or more like a control? And what was the probability that she was a case? And based on that probability, that score, she was then referred for further evaluation. And I'll just say that the score was calibrated to have a high specificity. So in ovarian cancer, you really want to have a high specificity because the vast majority of women do not have ovarian cancer. And you do not want to be sending women to biopsy, which is highly invasive for ovarian cancer, you know, at a rapid clip. You want to limit that. So the test was actually calibrated to have high specificity. And then the sensitivity was estimated under serial prospective screening. And it was estimated to be quite high under serial prospective screening. And the serial prospective screening actually happened in the context of a trial that was started in 2001. So a trial was done of this test. I want you to note this sensitivity because I'm going to talk about sensitivity measures in a couple of minutes. So here's the trial. This is the primary report. There were actually two screening arms. The one using the marker is the red arm. And it was not a significant mortality reduction. You can see it only started later in the time interval. So now I'm going to show you a non-proportional hazards test that was developed, one of several developed to address this kind of evolving benefit. And it actually was statistically significant and showed a different effect and a much more significant effect in the next 7 years. So this kind of gives you a sense of some of the methodology that has come out of the need to address the complexities of early detection. And we find ourselves exactly at this point here. By the way, ovarian cancer screening has been deemed to be ineffective as a result of that trial. And the US Preventive Services Task Force has recommended against it. And the test, the product that was approved by the FDA has kind of been disapproved by the FDA. And it's very unfortunate because there are reasons why the trial didn't succeed that may be overcome by new technology. I'm concerned that we have written off ovarian cancer screening, and ovarian cancer screening is typically diagnosed in late stage and is a major is a highly fatal cancer. So we find ourselves at this inflection point where we kind of can look back and see our efforts to date and recognize that we now are in a situation where we have cracked this code, where technology has cracked this code. And the consequence is that we just now have a host of new products that can not only biomarkers for cancer, but that are biomarkers for multiple cancers. So the idea is that with one blood test, you could, in principle, know whether you have, in one test case, up to 50 cancers. And so here, the kind of the juggernaut of the companies, very deep pockets from big tech, is Grail, and you can get the test if you have $950, but you're not clear that your insurance will pay for the consequences of the test. So bear that in mind. It's approved in New York. They differ, the tests are different. There's a new one that comes along all the time. I just have 3 here. These are the ones that had published when I did an earlier version of this talk, but you can see they have different numbers of cancers. They have different features that they're using, high dimensional features. So the methylation features are very promising because they help to identify the tissue of origin. The Detect A test from Thrive was the first to publish. They use mutations. They're looking for mutations that are common across cancers and proteins in the blood. And they do not indicate, that test does not indicate the tissue of origin. You have to go for a full body PET CT, which is not 100% accurate for every tissue. So the actual imaging technology that now comes into play is something that's important to know about as well. We won't get time to go into that today. All right, so Grail and Delphi looks at, Grail looks at the methylation patterns, Delphi looks at the fragment size distribution. We could never have thought that we would be here like 10 years ago. So what do we know about the tests? The first is that they do have non-zero sensitivity to detect cancer in one of these phase 3 retrospective studies. So we have here the 2018 paper about the Detect A, the Thrive test, which was then called Cancer Seek. And what I'm showing you here is where there were 8 tissues. And so this is the sensitivity per tissue. This is the sensitivity per stage. Some of the cancers were late stage. Ovarian was typically late stage. So you're seeing late stage sensitivity for ovary and early stage sensitivity for breast. And here is the Grail test, which was published later. They did the sensitivity for, it was 50 cancer types, but they showed the sensitivity for 12 pre-specified cancer types. And you can see also kind of a low, there's a training and validation set here. They do that in this paper. Relatively low sensitivity for early stage, high sensitivity for late stage, and pretty good tissue of origin accuracy, up to in the 90s% for late stage. Now, I want to just go back to this slide and note, okay, that these tests, they're not giving you a binary result. They're giving you a score, some kind of prediction, right? They're developed using various, learning algorithms on high dimensional data, right? And so they give you a prediction, they give you a score. So they have to be thresholded. So they're thresholded to provide high specificity, and they compromise with low sensitivity, particularly in early stage cases. So because they're thresholded that way, and they're actually very conservative, relatively conservative tests, they have a high positive predictive value. Right? The positive predictive value is if the test is positive, what's the chance you have cancer? And if you have a conservative test, you tend to have a high positive predictive value. Why I bring this up, this is a poster that Grail presented last year at ASCO, because they are now in the middle of a prospective phase 4 study. And they're going to report out again this year after waiting a year for follow-up. They report a very high positive predictive value, and that's very impressive. This corresponds to having to do essentially one unnecessary biopsy for every cancer detected. This is a very high positive predictive value. But we have to remember that that doesn't mean people will be helped, because with a very conservative test, you can maybe only find late stage cases, and you can have a high positive predictive value, but not actually be helping anybody. So the measures are meaningful. Okay, so I have a lot more material, but I'm going to show you just a few, half of my slides. I probably won't get to the end. I'll zip through the end just so that we have time for questions and so on. The first part that I'm going to focus on is, in my title, was measures and methods. So what we don't know about the test, we don't actually know the tests. We don't actually know about their diagnostic performance in a prospectively screened population. And we certainly don't know if they're going to help people, right? So these are key quantities that we absolutely need to understand before we can determine whether the test is worthwhile. But they're very hard to measure. So I'm going to talk about 2 proxy measures that people use. And I'm going to more or less, raise serious questions about them. And the last part of the talk is, how do we get these numbers? And the answer is, it's going to be very challenging and could take a long while. And so what can we do as statisticians statistically in the meantime? So that's the part I probably won't get a lot of time to go into, even though it's my bread and butter. But I had to stop because these measures are being promoted as part of what I see as a wholesale effort to promote the tests. And I think one of the roles that we as statisticians play in the broader community is debunking measures that are being purported to show something, like I just did for the PPV, that may not be indicative of what they're trying to show. So I want to talk a little bit about sensitivity. Now, sensitivity to detect cancer in a prospective screening setting, I talked about verification bias, is extremely challenging unless you biopsy at least some of the negatives. So there is a measure, and this was actually used in the ovarian cancer study that I showed, that is a proxy for sensitivity that is actually in wide use. It is referred to as sensitivity, but it's actually not. And so I call it something else. I'm calling it empirical sensitivity, as to distinguish it from true sensitivity to detect preclinical disease. So empirical sensitivity here at the bottom is simply, you take the number of screen detected cases divided by the number of screen detected plus interval cases. Obviously, it's going to depend on the interval, what your denominator is. But it's often cited for a 1-year interval because that's how often screening happens. For example, in the Breast Cancer Surveillance Consortium, which is the biggest, most authoritative source of data on breast cancer screening, the sensitivity is cited as 87%. It's empirical sensitivity. Yeah.
So what's interval detected mean?
What's that?
What does interval detected mean?
Between screens, clinically detected.
Series of screens.
Yeah.
Shows up.
Or even one screen. You could take one screen, and so what's happening is that the multi-cancer tests are doing a single screen and are reporting out after a year of follow-up from a single screen. But you could do it with BCSC has serial screens. Also, the National Lung Screening Trial, the NLST, reports out a sensitivity. And they've done it in different ways, but some of their numbers are empirical sensitivity. Okay. So what I want to do is I want to try to make the case that this should not be called sensitivity. And in order to do that, I want to show how biased it is for sensitivity. So for true sensitivity. So in order to do that, I'm going to write empirical sensitivity with a mathematical expression for these components, the probability of being screen detected and the probability of being interval detected. And those mathematical expressions will have the true sensitivity in them. So I can write empirical sensitivity as a function of true sensitivity, but it's also a function of other things. So basically, what's the probability that the cancer is screen detected at any given time? Here I'm showing you in the second trajectory. I have these individual level trajectories. What's the cancer probability that a cancer is screen detected here? Well, for a cancer to be screen detected here, it has to have onset before this time. And then it has to have a true positive screening test at this time. And it could have had onset in this interval or in this interval. So I have a sum over intervals of the probability of onset in that interval. And then depending on how many screening tests fall, negative screening tests fall before that time and the time of diagnosis, I also have a probability of those false negative screening tests. So this is essentially the expression. F is the density of onset. G is the distribution function of the latency or sojourn time. Alpha is the sensitivity. And you can see you can put these expressions together, but you see that alpha is in there. The true sensitivity is in there. And it's same for interval cancers. I develop an expression that has alpha in there. So the probability of having an interval cancer, having a screen detected cancer is a sum over all the possible intervals of onset. So before we get to the figure, I just want to note that these expressions on the previous page imply that this empirical sensitivity is a function of the true sensitivity, but it's also a function of the screening interval and that sojourn time distribution, G, and onset. So here, it's a function of the intervals, it's a function of the onset distribution, it's a function of the latency and the true sensitivity. And so what you can do is you can investigate the bias of empirical sensitivity for different values and see when it's really biased. So I'm sorry there's so much in this figure. Let me just tell you what I'm showing you. I'm showing you empirical sensitivity on the y-axis as a function of true sensitivity on the x-axis for different intervals, 1, 2, 3 years, and for different latencies. We've got 1, 2, 3, 4, 1, 2, 3, 4, 6, and 8. So the latencies go up, right? Going from red to pink. And so at the 1 year interval, you can see that the high latencies mean empirical sensitivity is very biased. Empirical sensitivity is an overestimate if you have a high latency in a short interval. Conversely, empirical sensitivity is an underestimate if you have a short latency and a long interval. But the bias is not constant over true sensitivities. The bias actually depends on what the true sensitivity is. So you can look at this, you can think about it, you can learn, you can think, if I see an empirical sensitivity, I know there's a caveat here. I can go to a chart, I can look it up depending on what I think the true latency is. So we went back to the Breast Cancer Surveillance Consortium data, and the estimate is 0.869. And we then solved this. What is the true latency under different sojourn time estimates? The sojourn time for breast cancer has been estimated over the years. Here are 4 papers. It's actually increased over time as the ability to detect, almost the definition of a latent breast cancer has changed over time. But if you take this number, say 4.6 to 5.6, depending on what we assume for those densities and those expressions, you can see that the true sensitivity is actually considerably lower than 0.87. So this gives us a way. So what am I doing? I'm just preparing to caveat when the multi-cancer companies publish empirical sensitivity after 1 year across cancers. We can look at the cancers and say, we know this is kind of a longer latency cancer. We suspect this is a shorter latency cancer, and we can think about the validity of those empirical sensitivities. Okay, so that's kind of what my point here. So we're kind of prepared, for these results to come out and be kind of popularized at, say, at ASCO this year. But really, we need to figure out ways to do better than empirical sensitivity. And this is actually still an open question, to do a better job of learning sensitivity in the prospective screening setting. And so I think there's opportunity here too. Okay, so let me go to the next measure that I'm concerned about, and that is the reduction, the ability to project the reduction in cancer deaths, because even if you have a high PPV, you might not be reducing cancer deaths. Okay, so a proxy measure that's being suggested by many, particularly those in the business, is to use the reduction in advanced stage at diagnosis. And this paper that's just online at Cancer Epibiomarkers and Prevention, randomized controlled trials for mortality in screening take forever, cost a fortune. Future trials with late stage incidence as a surrogate endpoint could substantially reduce these challenges. I don't know, a lot of these authors, Tim and Steve have worked in this area. Sana is a consultant for GRAIL. And indeed, what I wanted to show you before I go to that is to, first of all, GRAIL is doing a trial right now, the first randomized trial of a multi-cancer test, and late stage incidence is the endpoint of that trial. I'll show you in a couple of slides. But before I do, I want to just talk about what does this mean? What does it mean to say that late stage incidence should be a surrogate endpoint? It could mean multiple things. From a testing perspective, it could mean if we do a test for benefit and we do a test on late stage incidence and it comes out to be significant, then we're going to call that a win. But it could also refer to estimation. Are we going to use late stage incidence differences to estimate mortality differences? I'm not sure that that's what is meant here. There are two possibilities. You could use a reduction in late stage diagnosis as the endpoint, both for designing and estimating trials and analysis and kind of estimating the and this is your estimate of benefit. Or you could use the reduction in late stage diagnosis to project what you expect would be the reduction in mortality, right? So both of those are being suggested. So it's not 100% clear when people say use late stage incident as a surrogate endpoint, what exactly they mean. Because here's the GRAIL trial being done in the UK. And if you look at the last sentence, this will allow scientists to compare the stage at which cancer is detected between the two groups. So they're all being screened, but only half of them are being assayed and actually read and actually acted on. That's the trial. And they're going to compare the stage as the endpoint. And here's the number two, where this is actually from a group of authors, including authors from GRAIL, where they look at the reduction they actually look at the elimination of late stage disease. They say, if we could eliminate stage 4 disease, we would have a 24% reduction in cancer-related deaths at 5 years. If we eliminated late stage disease and distributed those cases eliminated from late stage equally over stage 1, 2, and 3, we get a 24% reduction. Okay, so what I'm going to show you in the next few slides is a general formula for doing that translation if there are two stages, early and late. All right. So if you have early and late stage disease, then your mortality at time t is going to be the integral over the incidence and the survival. So the incidence is PDF, and here I have this is 1 minus it's the survival CDF, not the survival function, it's the CDF. So people have to die by time t, people have to have been diagnosed and they have to survive less than time t. And if there's a late stage and early stage, I can decompose this survival CDF into a mixture for early stage and late stage. And so now I'm going to show you that if I have a reduction in P1, which is the probability, it's not P1, I've written it wrong. It's the incidence of late stage that's reduced, not the, it turns out to be equal to, it is actually a reduction in P1, but if I reduce this incidence of late stage by a factor alpha, so let's say I reduce late stage by 50%, alpha is 0.5, then my mortality reduction is this quantity times alpha. So my mortality reduction depends on what fraction of cases were originally in late stage, right? If only a minority of cases were originally in late stage, I won't get such a bang for my buck of reducing late stage by 50%. But it also depends on these two quantities, R1T and R0T. And these are the mortality, R0T is the mortality by time T if all cases were early stage. And R1 is the mortality by time T if all cases were late stage. So it's kind of the difference, it amounts to how different the survival for early and late stage cases is. And that also makes sense, right? If I move cases to early stage, but I don't improve their survival, then it's not going to help to take them out of late stage. And so this was done by a new member of my team, Lukas Owens, and we went through the SEER data and we looked at all these cancers and we used the formula to project reduction in late stage disease to reduction in mortality if you just switched out their survival. Why do we do this? Because we want to show that even for some cancers currently based on stage-specific survival, you can promise to reduce late-stage cancer, but you won't necessarily reduce mortality by that much. And these are cancers that are high on the list of multi-cancer tests because they don't have screening tests yet available. So we have to be realistic of what we can achieve with this idea that we will reduce late stage, which is not guaranteed. And so then what we did was we took this formula and we said, what if we used this as a surrogate to predict the mortality in 4 trials based on the reduction in late stage in each of the trials? So there's lung cancer, there's prostate cancer, there's ovarian cancer, and there's breast cancer. And so the orange line is the line from the previous slide. The orange circle is the late stage reduction and mortality reduction predicted from the model. And then the blue X is the late stage reduction and the mortality reduction observed in the trial. And the only thing you need to take away from this figure is that they're not on top of each other. In one case they are. And in this case, it's a little hard to say because there wasn't much of a reduction in the ovarian trial. So I just want to say that this whole idea is not necessarily going to pan out, but it's also a total oversimplification. Because if you think about ovarian cancer, for example, we have different types of cancers, and they're not equally represented in late stage and early stage. In ovarian cancer, there's type 1, which is less aggressive, blue and red, and type 2, which is more aggressive, green and brown. And I'm showing you the numbers from many years of SEER in each group. So in early stage 1 and 2, most of the cancers are type 1. In late stage 3 and 4, most of the cancers are type 2. So if we just put them together, the late stage curve will look like the brown curve, and the early stage curve will look like the blue curve. And by just moving from late stage, imagining moving from late stage to early stage, we're also imagining patients changing their type, which doesn't happen. So we really should move from, the brown curve to the green and the red curve to the blue. We should do it by type. If we're going to try to predict mortality reduction in this way, at the very least, we should do it that way. So unfortunately, we can't easily go back to the trials and see if that would give us a better answer, because the trials didn't always measure the biologic prognostic histologies that we need here. So what have we learned? to use a reduction in late stage diagnosis is not going to be correct if you add the actual reduction. If you saw the original figure, you'll see that even the predicted reduction was nowhere near the actual reduction. Reduction in mortality was nowhere near the reduction in late stage. And predicting mortality based on stage shift is not always going to be correct. But I do think that we need to think carefully about surrogate endpoints here, because the definition of a surrogate endpoint in treatment trials essentially requires a surrogate to mediate the effect of the treatment on outcome. And this may be the case for late stage incidents, at least it may be a partial mediator. We need to understand the extent to which it mediates the effect of screening on mortality. Okay, so I'm going to wrap up, and just in a couple of minutes, I'll just say a few words about the fact that clearly we need an understanding of benefit and harm. Late stage reduction is still aspirational because no studies have actually shown that there's a late stage reduction. And there's one screening trial, and it's hard to know whether there will be more and how long they will take. So as statisticians, I think that we can be useful here, because in cancer screening research, there's always been a mantra that you need a randomized trial with cancer-specific mortality as the endpoint. But that is reasonable if you have one test and plenty of time or money. But we have many tests, and I just showed you the multi-cancer test, but there's a host of single cancer tests. I just read about a new ovarian cancer test based on exosomes and a pancreatic cancer test out of UC San Diego. And there's tons of companies doing specific cancer tests because this code has been cracked. So, and the tests are already being made available. So a lot of our work has been in the last decades has been on modeling to fill in the gaps. And I'm not actually going to even hold you here to go through the next part of the talk, because it talks about modeling, and it talks about a model that we're doing to try to fill in the gaps. This is a very simple model that we did already, just to make it clear that we have many different prevalences of different cancers. And even if you have a test that has a reasonable performance across cancers, and even a reasonable reduction in disease-specific mortality, it doesn't mean that you'll necessarily get the benefit-harm trade-off that you expect. So this is just a shiny app where you can configure a test. You can not only put in the sensitivity, the correct localization probability, and the mortality reduction, but you can select the cancers to include in the test. Now, nobody is talking about which cancer should be in the test. So this was our idea, was to show that if you configure the test differently, you can get very different harm-benefit trade-offs. And we looked at how many are exposed to unnecessary confirmation tests, how many cancers are actually detected, and how many cancer deaths are prevented. So you can kind of look at harm-benefit trade-offs. But we don't know what the mortality reduction is going to be. And we have, in fact, cancers that we have modeled over the years, and we could potentially project mortality reduction based on existing models of screening modalities. We simply need to add a new marker to these models. But there are a whole bunch of cancers that we don't have models for. And so right now, we're trying to think about simpler models, maybe with additional assumptions, and trying to think about the minimal data to inform those models. And I'm going to skip through that. This is from my colleague Jane Lange at OHSU, where we developed a simple model, and we checked it against the National Lung Screening Trial, where we did it for lung cancer, and we were able to put in the extra inputs and figure out and project not mortality reduction, but a reduction in advanced stage disease in this trial, and see if we matched the observed reduction in advanced stage disease. So this is almost my last slide. I just want to say that I'm involved with multiple national panels that are trying to figure out how we're going to objectively determine the harms and benefits of these tests. And it's a tremendous conundrum, because in the past, we've only had one technology at a time. And the NCI has really stepped up to do large trials. And the most ambitious to date, right, was the PLCO trial, which screened for prostate, lung, colorectal, and ovarian cancer, with one modality for each. But now we have tons and tons of tests, and people are talking about basket trials. Remember, when you do a cancer screening trial, you have to have a sample size that permits you to get enough power for the deaths that you're going to observe and the difference in deaths, which is orders of magnitude bigger, smaller than the sample size. So your sample size has to be orders of magnitude bigger. So the UK CTOX trial was 200,000 women. So even convening one trial is going to be exorbitant. And that's for one product. Now, what are you going to do for other products? So I can tell you that I'm advocating, going to continue to advocate, not so much for trials, but for large, well-run cohort study, where we either use a selected technology that goes across cancers, and we use that, and maybe we biopsy some of the negatives, we follow for a few years, and we use that to really hone our understanding of natural history for these cancers, and then do essentially learn enough to be able to do credible virtual trials of multiple platforms. So bringing modeling into the evaluation process, because I don't see another way to do it. And then you can use the resulting models to, developed in the right way, in a way that is credible. They have to be developed in a credible way to project a range of plausible mortality reductions as these products evolve, and maybe to design future trials. So clearly we're talking about a critically important advance, but we also have a huge unsuspecting public. And I need to iterate at this point, as I said at the beginning, if you have $950, you can get a test, but what's going to happen afterwards? And cancer screening is not just about the test, it's about the follow-up and it's about the treatment. And all of that has to be covered if you're going to be advocating for a test. And currently there's no instruction, there's no direction for what to do after a positive test. So people will be essentially at the mercy of their health insurance plans. And so we're taking a defensive posture to make sure people are aware of the limitations of common measures that may inflate perceptions of benefit. But we really urgently need new ideas for methods not to replace, I'll never say replace trials, but to augment trials and to learn in the time frame that we need to learn to inform the public. And there will be uncertainties, but if we can learn in a robust way across those uncertainties, we can really inform the public. And it's not clear that these tests are necessarily to be used in the average risk population. Maybe they should be used in certain high-risk subsets, for example. We need to find the use case for these technologies. So these are collaborators. I've got one more slide after this, a quick ad. I just want to say Roman is at Fred Hutch. Jane is at OHSU. Both of them are extraordinary modelers. Boshen is a student who's will be graduating soon, a health economist. Lukas is an actuary who's part of my team, thankfully. Kemal is an economist at OHSU who we have enticed over to do health economics. And Yibai is a new graduate from UMass Amherst, and Noel Weiss is an emeritus epidemiology professor I've had the good fortune to get to know at Fred Hutch and UW. We have a couple of calculators, and I'm happy to share these slides. My ad is for the International Conference on Health Policy Statistics, which I'm co-chairing in January. This is a very student-friendly conference that is about a lot more than health policy, but has a health policy and health decision-making tilt. Wonderful people, lots of student support. We have a student travel award if you're interested in presenting a paper. A lot of diversity, it's international. We have international. We have all academia, government, industry. Everyone is welcome. And our invited session have closed, but contributed papers, if you go to the website, you will see the dates for contributed papers. And as I said, if students submit a paper and you come to present, there are travel awards for students. Scottsdale is lovely in January. We'd love for you to come. And I'll stop there. Thank you.
Questions, maybe? I can grab you the cube of.
Oh, come on up.
Yeah,
People in here. Or does it
I
move?
think it moves. I've never used one. Okay, cool. Excellent.
I don't know whether this works. Okay, it seems to be working. So
Okay.
wonderful talk. It's a very impressive review of the status quo here. So I have two questions. The first is the search on time distribution. So you showed a few results based on different estimates, and they seem indeed to be very different. I wonder, when you're trying to communicate this kind of bias in that sensitive estimate, do you present them all? Or are you expecting these updates to be different in 5 years? Or
Yeah, so I wouldn't present the first because that's from the trials. So mammography has changed a lot since the early trials. The last trial was done in the 80s. So in the 60s, 70s, and 80s, mammography has changed a lot. So the surgery time is basically the interval during which the sensitivity of the modality is not zero. And if it's modeled as a constant, it's the interval over which, you estimate. It's a little bit of an identifiability question because, modality and sensitivity of the modality actually play into the notion of detectability. And so if you say it's the detectable latent interval that detectable latent interval changes over time. I looked at the second two, 4.6 and 5. I think those are more in this range of what we're talking about. This is including in situ cancers. But even models done over the same contemporary period, because I showed 4 models, there's 40 models, okay? So even models done over the same interval don't always give the same answer. It's really hard for the layperson to know. So we tend to be selective in the models that we kind of put in our papers, the ones that we think are reasonable.
Mm-hmm.
Yeah, but it does get down to second order stuff like assumptions, data, and so on.
thanks.
Yeah, well, let me just say one more thing.
Yeah.
And whether they've verified that their model is identifiable, because these kinds of models have identifiability issues, and most papers do not verify identifiability. Identifiability can be a theoretical concept, but it also is a practical concept because you can have a model that's identifiable in one data set, but not in another. It's really important because you're estimating these latent transitions. In addition, potentially, some of them also estimate sensitivity to assure that your model is identifiable.
Yeah, that's that issue I come across a lot. Some people just do Bayesian and then present a interval, which involves some prior knowledge, but yeah, it's a good point. A second question is about, so this is a more naive question, I guess, from the practical point of view. You said it depends on what to do after the screening, right? So the more valid outcome, so endpoint is mortality. I wonder whether this kind of evaluation should be done whenever a new treatment is coming out, because that may be very effective and screening suddenly become very attractive. I wonder, I did not see a lot of interaction between the treatment kind of thing side to the screen side. I wonder, how should we?
So there's I love that question because we actually have done some work on this. We've done 2 papers and we have a third one that Kemal is primary author on. So basically, if we could, so it's a very interesting modeling question, right? If we have better treatment for late stage disease, that will make screening less effective in terms of reduction mortality relative to control. There's just It may not make it relatively less effective, but in absolute terms, it will be less effective because there's fewer lives to save once you're treating late stage cancer as well. Now, it's complicated because if you're screening late stage cancer as well, you're also treating the late stage cancers that happen later, right, in early stage disease. So it's a little complicated, but essentially, if you have better treatment for early stage, screening effectiveness will be enhanced. And you know, we have some models where we've tried to implement this. If anyone would be interested in looking at it further, because we have used a stage shift representation for predicting mortality, and we decouple the stage, the effect of screening. We say the effect of screening is on stage, and the effect of treatments is on post-diagnosis survival. So we have a simple representation for how it might work. Yeah, no, great question. We have been very concerned about that. But the only US breast trial is 1960s. Treatments have totally changed. Yeah. So. Thanks for staying, everyone. Thanks for not falling asleep.
Why don't we
Thanks
thank
for showing up.
the speaker?